Hey, pre-cal kids, this is Mr. Beck. Today we're going to be talking about the sum and difference formulas for sine, cosine, and tangent. So what do we mean by sum difference formulas? It comes back to a question that I have. Is it true or false? Is the sine of 30 plus the sine of 60 equal to the sine of 30 plus 60? It's this concept of does the distributive property apply to trigonometry? And I know a lot of students, they look at this and they go, oh yeah, it makes sense that this is what's going on. And the answer is actually a big resounding no. And you'll see me write this on your papers if you do this. I mean, you might have already seen me write it on your papers. Sine of 30 is 1/2, the sine of 60 is square root of 3/2, and those do not combine into the sine of 90 degrees. So when I look at the second question I have here, is it true or false? Can we do the same thing? Can you add those two angles together just to get 90 degrees? And the answer one more time is going to be absolutely not, especially because the cosine of 15 is positive, cosine of 75 is positive. There's no way that positive plus a positive will ever equal 0. So a big fat no, this is false. All right. So our goal is, well, what is the sine of 30 plus 60 degrees? How can we write that out? Or more specifically, we have a formula, which I am going to tease you with right here. So we have a formula for the sum and difference angles that we're going to need to know. And we're going to need to memorize this pretty well. So the way that it's proved actually goes back to triangles. So what I'm going to do is just really highlight two triangles. And I know it's kind of hard to just look at this right from the beginning and say what's going on. Our goal is if we have a point, and the point I'm going to re-highlight right here. So if I have the point 1, 0, and if I have some point on the circle, which is going to be alpha minus beta. Now that alpha minus beta is better drawn where if we have a certain alpha, and I'm on the second triangle, and a certain beta, that's going to create this triangle right here. So with these two triangles, what we're going to say is these two triangles are congruent. We can have a little bit of fun geometry review and show why they're actually congruent. And the reason is side angle side, because the radii are the same, and then the central angle is the same, which is alpha minus beta. So this distance is equivalent to this distance. And that is going to be the beginning of our proof for why this is true. Now we are going to need points 1 and points 2 that we're going to be referencing along with 1, 0 and 0.3. So the distance between A and 0.3, if we use just pure distance formula, x2 minus x1 squared plus y2 minus y1 squared. And I'm going to go ahead, pause if you want to take a look at this a little bit closer. I'm going to go ahead and zoom in on my work because I wrote kind of small. So equals the distance between 0.1 and 0.2. Once again, x2 minus x1 squared plus y2 minus y1 squared. Now we will square both sides to get the expression that I'm underlining right now. Now we have some foiling that we can do. So that would be the first binomial foiled, then plus the sine squared, which is already there. And then we have two different foilings that occur. I think I went a little too far on that, so let me go back. So I have the first one foiled and I have the second one foiled. And in doing so, I could do some nice simplification. So the first one, what you see in green is equivalent to 1 because cosine squared plus sine squared is 1. What you see in blue, I'm underlining now, we have the cosine squared plus the sine squared, which equals 1. Then we have the pink, which is sine squared plus cosine squared equals 1. So we're really using Pythagorean identities on this quite a bit. And then I have some algebra that I simplified down to because what's happening is 1 plus 1 is 2. We got 2 on the other side by those combining together. And then if we divide both sides by -2, we get the cosine of alpha minus beta equals cosine alpha cosine beta minus sine, or plus sine alpha sine beta. So a lot of people are like, yeah, that proof is neat, but I don't care. It's honestly really important for us to be able to understand why our formulas work. I'm not a fan of somebody saying, here's a formula, use it. And I'm like, I don't know what this is for. What do I do? So it comes down to, do you understand what that formula is and how it applies? Now this is an equivalence that we're going to be using. So cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Follow along with what happens if it's not a minus, what happens if it's a plus. We can easily remedy that by saying, well, a plus is minus the negative. So this would be cosine of negative beta. Sine of negative beta if we apply the formula. Once again, cosine alpha, cosine in this case, negative beta, plus sine alpha, sine beta, which cosine of negative beta is equivalent to cosine of beta because it's an even function. So let me change colors on you. So this is an even function. So that's true. And then we have sine of negative beta is negative sine of beta because sine is an odd function, which then if we do the arithmetic, we bring that negative out in front. So we have cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, which, as I teased you before, is what leads to this expression. We will lump it together into one expression. Cosine alpha plus and cosine alpha minus beta turns into cosine cosine minus or cosine cosine plus sine alpha sine beta. What I'm going to encourage you to do is every time that we go to use the formula for the very first time, I'm going to have you write out that cosine alpha cosine beta plus or minus sine alpha sine beta according to the situation. So how do we apply it? Well, now how do we apply it? We're going into, let's see, what all angles do we know? We know the cosine of 0 degrees, we know the cosine of 30, we know the cosine of 45, we know the cosine of 60, we know the cosine of 90. Well, what about, and I don't think I drew that as accurately as I should have, but that's okay. Let's go ahead and say that's our 30 degrees. So that means we don't have that one yet. But now we're about to, because we can use 30s and 45s and 60s to come up with 15 and 75. So now we're going to work with all of the angles that are 15 degrees apart. So to do that, what I have up here is some helpful trig fractional relationships. Not anything incredibly difficult where we say, okay, pi over 3 is equivalent to 4 pi over 12. Pi over 4 is 3 pi over 12, but putting everything in terms of pi over 12 tends to be beneficial because then when we're working with our 15 degrees, and if you remember, 15 times pi over 180 does give us the pi over 12. So anytime that we're working with the 15 degrees, we can always take everything to our common denominator of pi over 12. So let's go ahead and do that. If I want to know the cosine of 15 degrees, what I first do is say, how can I make 15 degrees out of 30s, 45s, and 60s? Well, 15 degrees, I chose 45 minus 30. What if somebody said, hey, Mr. Beck, I did 60 minus 45? Great, that'll still work. I didn't show that for this one. I mean, if you really want me to, actually, I will at the end. But let's go through the first one. So cosine of 15 degrees, if I treat it as cosine of 45 minus 30, cosine 45, cosine 30, plus sine 45, sine 30. We know the cosine of 45 is square root of 2 over 2, cosine of 30 is square root of 3 over 2, sine of 45 is square root of 2 over 2, and sine of 30 is 1/2. We do some arithmetic. Square root of 2 times the square root of 3 is the square root of 6. And then we have square root of 2 times 1 is the square root of 2, and all over the common denominator of 4. So turns out that cosine of 15 degrees is square root of 2 plus square root of 6 all over 4. Now, what if somebody said, Mr. Beck, but I chose the cosine of 60 minus 40? Great. That would be cosine 60 degrees. Cosine, that's not 40, it's 45. Should have caught that earlier. Cosine 45 degrees, and then plus sine 60, sine 45 degrees. So cosine of 60 is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Sine of 60 is square root of 3 over 2. And then sine of 45 is, wow, Mr. Beck, that was going too quickly. That would be 1/2 square root of 2 over 2. Therefore, once again, now I get the square root of 2, bad handwriting, square root of 2, still bad handwriting, plus the square root of 6, all divided by 4. So don't make that mistake. Cosine of 60 is 1/2. But anyway, we still get the exact same fractional relationship despite the fact that we started and did this in a different way. But that's actually why I love math so much, that it's not just about doing math one way, it's about it all works and we can see those relationships and how we work with it. And again, the reason why it works goes back to that proof that a lot of people don't really care about, which is so sad, but it's that proof that it's always going to be true. But anyway, cosine of 5 pi over 12. What if I did this as 2 pi over 3 minus pi over 4? And kind of looking at our fractions, how did I get 5 pi over 12? Well, I thought about it as 8 pi over 12 minus 3 pi over 12. So 2 pi over 3 minus pi over 4. You can see I did that. Cosine 2 pi over 3, cosine pi over 4, plus sine 2 pi over 3, sine pi over 4. Went through all the different values, and I get the expression square root of 6 minus the square root of 2, all divided by 4. If I would have done this as, well, maybe pi over 6 plus pi over 4. So pi over 6 is, if you look at this as 2 pi over 12 plus 3 pi over 12, then sure, let me go ahead and change this to a green color. So if I change this to a green color, then we get cosine, cosine. Now this is minus because it's cosine plus, but then it's going to be minus sine, sine. So square root of 3 over 2, square root of 2 over 2, minus 1/2 square root of 2 over 2. And I get that exact same expression, square root of 6 minus square root of 2, all divided by 4. Now for C, cosine of negative pi over 12, I decided to choose 2 pi over 6, or sorry, 2 pi over 12 minus 3 pi over 12. You get that? So cosine, cosine plus sine, sine. Do all of the different trigonometric values, and I get square root of 6 plus square root of 2, all divided by 4. Now that answer should be the same as the very first one because this is pi over 12, and cosine of pi over 12 and cosine of negative pi over 12, because cosine is an even function, those should be the same value. So it's neat that the numbers actually do work. Now we're going to kind of go backwards. We're going to say, what happens if I have the cosine, cosine plus sine, sine? Well, you are required to know that, hey, I've seen that relationship before. Cosine, cosine plus sine, sine is really the difference of angles for cosine. And now cosine of 60 degrees is 1/2. For part B, so once again, I see cosine, cosine minus sine, sine. As that's minus, it's going to be the sum of angles for cosine. So the cosine of 45 degrees, square root of 2 over 2. On to our third example. Now I have sine, sine minus cosine, cosine. Ooh, we're throwing you for a loop. Now to do this problem, this is not cosine, cosine minus sine, sine. So what we have to do is factor out a negative and then flip the order. So now it's the negative of cosine, cosine minus sine, sine. So now if I add those two angles together, I didn't actually show that. So this will now be the negative of the cosine of 100 plus 110. So that would be the negative cosine of 210. Cosine of 210 is negative square root of 3 over 2. So the opposite of that is the positive square root of 3 over 2. And for part D, I love this kind of problem where first thing is I've seen cosine, cosine minus sine, sine. So it's the sum of angles formula for cosine, which gives me cosine of 75. And it's like, oh darn, I don't actually know that, but I can actually break that into 30 plus 45. So cosine, cosine minus sine, sine with those angles gives us the square root of 3, or square root of 6 minus the square root of 2 all over 4. If you need me to show that, that's totally okay, but it's true. Sorry, if you need me to see that, honestly, prove it, see what happens. Now, we have an identity that in many ways we've talked about before. It comes down to this triangle that based off of the triangle that I've drawn here, if I have an angle theta and I'm calling that y, x, and r, which is pretty standard, sine of theta is opposite of hypotenuse, which is y over r. Now, what if I didn't want to look at theta? What if I wanted to look at 90 minus theta, which is that other angle? The cosine of 90 minus theta is adjacent over hypotenuse, which is also y over r. So the sine of theta is equivalent to the cosine of 90 minus theta. And that's because cosine really means the complementary sine. So we've been calling it cosine all this time, but it really represents the complementary sine. What that means is if I have a certain angle, sine of 50 degrees is equivalent to the cosine of 40 because those angles are complementary. Sine of 2 is equivalent to the cosine of 88, once again, because those angles are complementary. So we can prove this by using the difference of angles formula for cosine. So cosine, cosine plus sine, sine. Cosine of pi over 2 is 0, and sine of pi over 2 is 1. So we get this actually equals sine of theta. Now, I decided to turn part B into, hey, let's verify this identity is true. So I'm turning this into a little bit more of a proof style, where If I'm trying to prove this is true, I am going to use what I did over here to help me. The sine of some angle, let's just, let me highlight this in the color other than blue. The sine of some angle, kind of like what I have here, the sine of some angle is equivalent to the cosine of pi over 2 minus that angle. So what I did was I put that angle in right here. So the cosine of pi over 2 minus that angle. So then I distributed out, or distributed the negative, which gives me cosine equals cosine, check, QED. So I proved what I wanted to. So the sine of alpha minus beta, so if I want to find the sum and difference angle formulas for sine, I could use what I just did and said the sine of alpha minus beta is the cosine of pi over 2 minus that angle. This is some creative reworking. So let's go ahead and distribute the negative, but then regroup it over here. So now I could use the sum of angles formula for cosine. So I have cosine of the first angle, cosine of the second, minus sine of the first, sine of the second. This is where we're going to once again reuse and resubstitute in that the cosine of pi over 2 minus alpha is the sine of alpha, and the sine of pi over 2 minus alpha is the cosine of alpha. So grand story or grand idea behind this is we have the first of the two angle formulas for sine. So it's sine of alpha minus beta is sine cosine minus cosine sine. And then if we did the same thing that we did before, I'm trying to remember if I have it written here. If I want to say what happens if it's a plus beta, we could turn this into minus and negative beta. Then the cosine ends up being the same, but the sine ends up being opposite, which changes the sign. Now, let me go ahead and just rewrite all of the formulas that we know so far, just to write it out clearly. The cosine of alpha plus or minus beta is cosine alpha cosine beta minus or plus sine of alpha sine of beta. And then the sine of alpha plus or minus beta is going to be sine alpha cosine beta plus or minus cosine alpha sine beta. Now, the cosine changes the signs, but the sine keeps its signs. So that's the way I remember it. Sine keeps the signs. Yay, and we're happy about that. All right, so let's kind of apply this in the same way that we just did the other one. That if I want the sine of 19 pi over 12, first we could break it up into 10 pi over 12 and 9 pi over 12, which gives us 19. So sine of 5 pi over 6 plus 3 pi over 4. Sine cosine, keep the sine, cosine sine, and then plug in the individual values that we get from there. And if you notice, all of these problems are very similar to what I gave you on the review packet way back for 6.1 to 6.3, because really this is the application of all those individual little details. Well, that's why I gave it to you. Sine of negative 17 pi over 12, if I treat that as negative 9 pi over 12 and minus 8 pi over 12. Sine of the first angle, cosine of the second, minus, and it's minus because it's sine, which keeps its signs. Cosine of the first, sine of the second. Find all the individual values and put it together as one big expression. So what you'll find is any of the 15-degree angles have some form of square roots of 2s and square roots of 6s all over 4s. The sign of each one of those is going to be different just based off of the location. Now, this is kind of like the second type of problem where I'm seeing sine, cosine, minus cosine, sine. That tells you that since it's sine, cosine, cosine, sine, it's the sum or difference. And it'll be the difference because sine keeps the signs. And then sine 60 degrees is square root of 3 over 2. So now we get into some identity work here. You can see the identity that I have here. My goal is to take one side and make it equal to the other. I'm going to choose to work on the left side because that is two angles combined into one, which is a little bit more complicated than anything else. We have to first get rid of that. So cosine, cosine, plus sine, sine. Now we can break that into two terms, the first term plus the second term. The first term, we have cosine over sine of alpha, cosine over sine of beta. Second term is sine alpha sine beta over sine alpha sine beta. So we proved what it was that we wanted. Now, the second one is a proof, but the idea behind the proof is this is really establishing the sum and difference angles for tangent. Just ignore, let me go ahead and take those off at the moment. So take those off at the moment. So tangent is sine over cosine. And then we could use the sine as sine alpha, sine cosine plus cosine sine over cosine alpha, cosine beta minus sine alpha, sine beta. So how is that equal to tangent of alpha plus tangent of beta? Let me go ahead, throw in another step. This is going to be, I won't actually require you to prove this, but if I multiply both the numerator and denominator by 1 over cosine of beta, and then also the um, cosine of alpha, I believe. So cosine alpha, cosine beta. If I do that to both numerator and denominator, so cosine alpha, cosine beta, what ends up happening is for when I distribute, and I really probably should do this as sine alpha, cosine beta over, now that's too much to write. I hate to do it that way, but I'm kind of on a time crunch. Anyway, we have sine over cosine, which gives us the tangent, but then we have the cosine beta over the cosine beta, which ends up canceling or reducing, which is 1. I have sine beta over cosine beta, and the cosine alphas cancel. In the denominator, I have both cosine alpha and cosine betas canceling, which gives us the 1. And then on the other term, sine of alpha, sine of beta over cosine alpha, cosine beta is tangent alpha, tangent beta. So that's why it's equivalent. But anyway, sorry to rush through that proof. How we apply it is, if I want to know the tangent of 75 degrees, it'll be a tangent of 30 degrees plus 45 degrees. So tangent of the first, tangent of the second over 1 minus tangent of the first, tangent of the second. So please, please, please don't ever forget these formulas. Now, what happens if the signs are different? If it's plus or minus, then that's a minus and this is a plus, and that's because sine keeps its signs, which is why our numerator is the same. Cosine flips the signs, which is why the denominator is not the same. So that's a good way of remembering which approach that we're going to be taking to it, which one is going to maintain the signs and why. So on to some more applications and some more problems. My goal here is to find the tangent of alpha plus beta. Now, this time I'm not given certain angles. So now I'm giving a cosine relationship. And so let me choose a color that I have not used on this paper. So if my goal is to find tangent of alpha plus beta, let me first start by saying is tangent of alpha plus tangent of beta over 1 minus tangent of alpha tangent beta. Great. Do I know tangent of alpha? No, I don't. What I know is cosine of alpha, and I'm told what quadrant it is. So that's a creative way of saying it's in quadrant 2. So what you can see here is I have now drawn out my triangle. Remember that the cosine ratio is adjacent over hypotenuse, and we knew that it was in quadrant 2. We could use Pythagorean theorem or the x squared plus y squared equals r squared to figure out what the y value is. Now the y value is going to be positive because we're in quadrant 2. Therefore, the tangent of alpha is 2 squared root of 5 over negative square root of 5, which is just negative 2. So the tangent of alpha is equivalent to negative 2. Now, what about tangent of beta? This tangent of beta that we have here. Well, what do I know about beta? Over here, I'm told that beta is in quadrant 3, and the sine ratio is negative 4/5. So we're going to draw triangle B, or triangle with beta, and we know the sine ratio is opposite over hypotenuse, and we could use Pythagorean theorem again. And this is a well-known 3, 4, 5 triangle. So we could say the x value is negative 3. So the tangent of beta is 4/3, and that's what I'm plugging in here. So tangent of beta, tangent of beta. Now, if you remember, one of the things that I told you is a nice approach to these problems is let's clear the fractions by multiplying by the LCD over the LCD, which is what I did here. And when I do that, I have negative 2 times 3 plus 4 over 1 times 3, and then minus minus, which is plus, 2 times 4, because those 3's reduce. Now, this makes it a lot easier to add, so we get negative 2/11. on to the next problem. Next problem ends up being really, really complicated at the end. I will try to avoid to do that to you on anything important. But anyway, if I want to know, once again, tangent of alpha plus beta, because those are my overall directions, I'm going to start by saying, I didn't write it here, so I'm going to start by saying this is tangent of alpha plus tangent of beta over 1 minus tangent alpha tangent beta. So I'm going to do the same thing that I did before. This time I'm told tangent of alpha is 5/12, which makes life a lot easier. So I can replace the tangent of alpha immediately with 5/12. But I don't know the tangent of beta. So to find the tangent of beta, let's use the information that they give us. We are told beta is in quadrant 4, and the sine ratio is -1/2. Hopefully some of you recognize what's going on right there already, but in case you don't, let's go ahead and draw out the triangle. So the sine of beta is opposite of right hypotenuse, which if we do x squared plus y squared equals r squared, we can figure out that x equals the square root of 3. Tangent is 1 over it's y over x, which reduces to negative square root of 3 over 3. Now this is a problem that we really could have said, wait a second, sine of beta is -1/2 in quadrant 4. If sine of beta is -1/2 in quadrant 4, then that beta must equal -30 degrees or -π/6. So the tangent of -π/6, I can just cut to the chase and put that right there. Or I could go through the triangle. Doesn't really matter, and that's the beauty of mathematics. Then let's multiply by the LCD, which is 36. And when we do that, we have 36 divided by 12 is 3. 36 divided by 3 is 12. 36 times 1 when we distribute, and then the 36's here are going to reduce. Now I get an expression that looks like this, which, you know what, I'm going to be comfortable with. I'm going to be comfortable with because in order to rationalize this, it gets incredibly crazy. And it's not worth it right now because we have a value, and finding that value is really more important in my opinion. Moving on to problem number 9. Now our problem looks this way, and a lot of people freak out about this, but it's really the same kind of problem. My goal is to find tangent of alpha plus beta. Well, this time my goal is to find sine of alpha minus beta. How do I know that it's sine of alpha minus beta? Well, remember the inverse sine gives you an angle. The inverse tangent gives you an angle. This is a more consolidated way of giving us information than what we have in example number 8. So it's a shorter approach to it, what it looks like, but we can do the problem still in the exact same way. So our overall problem, once again, is sine of alpha minus beta. So if I wanted sine alpha minus beta, sine alpha cosine beta, keep the sine, cosine alpha sine beta. Well, the sine of alpha, we really know because they kind of tell us that already. The sine of alpha is -4/5. We don't know the cosine of alpha. So to find the cosine of alpha, we should draw out our triangle in quadrants, what I call -1. So the sine ratio is opposite of hypotenuse, or y over r, which tells us the x value is 3. So the cosine of alpha, which is what we need in the second portion of this, is a +3/5. What about the second angle, that what we call beta? Well, we know the tangent ratio is 3/4, which tells us we have to be in quadrant 1 because our tangent's positive in quadrant 1, or the ratio is positive in quadrant 1. So once again, the radius is 5. So the sine, or the cosine of beta, which is what we have first, is 4/5. And then the sine is going to be the opposite, which is 3/5. So now I have -16/25 minus 9/25, which gives us -1. For part B, once again, it's going to be the tangent of one angle plus another angle. So tangent of alpha plus beta is what we're going to call it. Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. So how do we find the alpha? We don't necessarily need to know alpha, but we know the cosine ratio is 4/5, which tells us quadrant 1. We could find the y value. Beta, the sine ratio is -5/13, so -5/13, which tells us quadrant -1. And we could use Pythagorean theorem, or this is right, the special right triangle, 5, 12, 13, or Pythagorean triple. So tangent of alpha is 3/4. Tangent of beta is -5/12. over 1 minus 3/4, negative 5/12. You see I multiply these by 48 over 48 and do the arithmetic to give us 16/63, which is kind of cool that the sum of those angles ends up being like a nice fraction. Last but not least, we have algebraic approaches to these problems, where what you could see here is what happens if I don't know the ratio. I'm just going to generically call it u and v. So we still draw it out. Tangent, inverse tangent of u, so opposite over adjacent, gives us an angle that we're going to generically say is quadrant 1. The Pythagorean theorem allows us to say that that is the square root of u squared plus 1. So the cosine of alpha, which is coming from the triangle, is going to be adjacent over hypotenuse. And then the sine of alpha, that's the sine of alpha, is going to be opposite over hypotenuse. And let me change colors. So that's what happens if I have my second angle, which is the inverse secant of v. So the inverse secant of v, remember with inverse secant, we have to put the absolute values in there. So the inverse secant is radius over x. So we can find the y value by doing Pythagorean theorem, which is what I have over off to the side. So the cosine of beta, which is what I'm trying to find, is going to be adjacent over hypotenuse, so 1 over the absolute value of v. Sine of beta, which is what I need for this portion, is going to be the opposite over the hypotenuse, which is square root of v minus 1 over the absolute value of v. And then we can combine it together into one big happy fraction. So, wow, that was a lot. There's a lot of detailed math specifically at the end. So please, please, please go back, and if there's anything you didn't understand, slow me down if you really want to, because the goal is you understand. Remember, understanding is our master quest. So signing off. Hope everybody has a great weekend.